Chapter 4, we looked at relationships between numerical variables. And so we had an X numerical variable and a Y numerical variable, and we put them together in an ordered pair and we plotted them on a Cartesian plane. And what we were looking for is the strength of the linear relationship. We've got this new correlation coefficient, statistics, R, is what we calculated back then. We wanted to know if there was a relationship, particularly a linear relationship between two numerical variables. In this test that we're going to do today, we're going to see if there's a relationship between two categorical variables. And so, for example, the first categorical variable could be males and females, not numbers, qualitative data. And then they ask these individuals, some males, some females, you can see how many total. They asked, are you happy in your marriage? And they gave them these three responses. They said, very happy. That's one thing they could say. They could say pretty happy, or they could say not too happy. Okay, go ahead and put in the chat, who's happier on average in their marriage without looking at this data, just your sense, right? Are males or females more happy in their marriage? Enter your response, male, female, into the chat. Neither. Okay, so this data is data taken from the National or the General Social Survey. It's done every couple of years or every years, and they give surveys on all sorts of items in life to adults in America, and then you've got this huge data set. And then you can take this particular data set had only 24,000 individuals in it, but it's huge. It's huge. Okay, so what we're going to do is we're going to try to answer this question, which is who's happier in their marriage, but we're going to then see if the differences that we observe are statistically significant. So I'm going to show you how to calculate conditional proportions here so that you can decide which group is happier. Okay, so the first thing you have to do is you have to calculate these totals. This is it's in the margin, right? A marginal total. Same thing here. We're going to be calculating proportions, and that means we're going to take one number, the number in category, whatever the category is, and divide it by the total in the sample, and that's going to give us a rate. And we can convert that rate then into a percentage. We call the rate the proportion, or relative frequency, we called it earlier. Okay, so let's first add up all the numbers in each row, in each column, and that's the first thing we need to do. Now, a couple of things in here, just like when we were looking at numerical relationship between two numerical data, we identified the independent and the dependent variable. We're going to do that the same thing here. It's important because we're going to identify our conditional proportions based on the independent variable. So we have to ask ourselves, which variable would explain the other? Which one would we select that could say, oh, if we knew that they were of this category, then that would explain. Okay, so in this one, it's pretty clear. The male here would be the independent, because probably what we're going to do here is we're going to compare the difference between males and females on this issue of marriage happiness. So gender would be the independent variable, and the dependent variable would be the response to this variable over here, which is the marriage happiness response. And they can respond in one of three different ways. The first thing that you notice when you look at this data is that there are very few individuals, male and females alike, that indicate that they're not happy in their marriage. I guess if they're not happy in their marriage, then they wouldn't be married. They'd get a divorce. But others just say pretty happy. Most of the others, you can see overwhelmingly either very happy or pretty happy. All right. The first thing we're going to calculate here is just the marginal proportions, because if we convert the marginal proportions into percentages, then we can talk and describe the data set in a little bit more detail. So for example, if we took the 15,551, which is the total number here, and we divided it by the total, 24,455, then you would get a decimal that you could convert to a percentage, and it would look like this. I'm just going to round it to 3 decimal places. So you can say that about 33, 34% of all respondents would say very happy. About 2/3 would say very happy in their marriage. Good number. If you can continue, I already have that total. 8185 divided by the 24, 455, we get 0.33, we'll call it 5. So about a third. A third would respond that they're pretty happy in their marriage. And then if we take the 719 and divide by the same, it's a very small amount, right around 3%, say that they're not happy. But these are the percentages or the proportions that we're calculating, and we're putting them in the margin of the table. So these are called marginal proportions. So this is one of the things that you're going to focus in on, that word right there. Calculate in these, we call these contingency tables. And every one of these numbers, we have 6 frequencies and or counts. These are actual individuals that responded this way. All right, now down here, we're going to take the 11606 and divide by the total as well. And then without calculating this one, we know that it's 525. These two have to add up to 1. All right, so what we can say here then is that 47.5% of all of our respondents are male. And we can say that 52.5% of all of our respondents are female. So slightly more females than males filled out this survey. Okay, now the last one is, this is the most important one, because this is the one that's going to tell you if there's a difference between the two groups that we're comparing, males and females. Now, because we're comparing males and females, we're going to divide every one of these numbers by the male total, the 11606. We have more females than males. We're going to divide all the females by the 12849. We have more females than we have males. So just a higher frequency does not necessarily mean that females would respond a certain way over males. So we have to divide by the number in the group. So we're going to calculate each one of these decimals here, and these are going to be known as the conditional proportions. So we're not calculating proportions on the margin numbers, we're calculating on the actual category numbers. So 7609. All right, so what you can see here is that you have 62% versus 64%, 62 versus 64, fairly close, but there's a little difference. So we observe a difference here. Our job today in the next section where we're going to go is we're going to see, is that difference that we observe, is it statistically significant? And even when you have a small difference like this, if you have a huge sample size, then your results can be statistically significant. All right, so let's do these here, 37, 38, and then 4447. So 35% versus 32%, we're still seeing about a 3% difference there. All right, now this last one is, not only do you look at the individual percentage points difference, so 32% versus 35%, 3% difference, 66%, 62%, 4 percentage points different. That's one thing you look at, but you also look at the relationship to one another. And even though 2.2 and 3.6, that's only less than 2% difference, 2 percentage points. What's important here is that this number here is about 1.5 times larger than this rate here. So when you go up to 1.5 or 2 times as high, that's a fairly significant difference if we're looking at the rates here. And who's not happy? Well, females are not happy more than males. Males are very happy at a higher rate than females. So based on our look at just these conditional proportions, and these are the numbers that you're going to look at, you see some differences. Males tend to be very happy at a higher rate than females, and females tend to be not happy, not too happy at a higher rate than males. So based on this, we would say that males are happier in their marriage than females, based on this, based on how they responded, which was not what we thought. It was not our intuitive when we were thinking about this problem. I think everybody said females are happier than in their marriage. And then based on this, maybe that's not the case. Okay, so what we're doing here is we're describing these different subgroups of the population. We've got this big group. It's one sample, one big sample from a population. In this case, the US population, 330 million is the sample size. And then we take this sample, and this sample is huge. It's got a sample size of 24,455, but from all of those. And then from that one sample, we have all this data, several variables on these individuals who participated in this sample, in this study. And we broke them down into groups. Well, first of all, we broke them down into males versus females, put them into two groups. And then we broke them down further as to how they responded to the question, are you happy in your marriage? So one sample, but then we take the data, we've got lots of different variables on them and break it down into a table like this. All right, so men seem to be happier in their marriage. And we say that because they're very happy at a higher rate than females. And females are, almost twice as likely to respond that they're not too happy in their marriage. All right, so this is it for section 4.4. You're going to be asked to calculate these marginal totals, and then the conditional proportions, and then say something about the conditional proportions. All right, if we have time, we'll do this other one here. This is a neat example on death penalty cases in Florida over a period of time, but it's another problem from section 4.4. All right, now just think about that last example with all of these proportions, and we observe some differences in how they would respond. And now what we're going to do is we're going to run the hypothesis test that goes with that. So here is section 12.2, which is very closely related to section 4.4. One builds on the other. The things that you did in 4.4, you're going to be doing in section 12.2. All right, so here are the 5 steps. We'll give you the 5 steps of a hypothesis test. Another thing that you're going to see here is you're going to have a new distribution. So we have the Z distribution, we have the T distribution with the degrees of freedom equals n minus 1, and now we have another one. And okay, it looks like this. And so you're going to get a new table. I guess I didn't put that table in the in e-learning yet, but I'll put it in there after class. And this one comes with, it's an entire family of distributions as well, like the T distribution. So you need to specify the degrees of freedom for each distribution. And the chi-square table is read in a way very similar to the T table. Find it later. Okay, let's do the hypotheses. And for this test, in that last example, we had 6 different proportions that we could calculate. Here they are: 1, 2, 3, 4, 5, 6. 6 conditional proportions in a contingency table. So we have to think about this in a different way. And remember, I said at the beginning that we're looking at comparing to see if there's a statistical difference between 2 categorical variables. And so the way that we're going to write this hypothesis is in this way. The row variable and the column variable are independent. If they're independent, the knowledge of whether a person is a male or a female gives us no information about how they're going to respond to this marriage happiness question. So in our case, we're going to say variable 1, which is gender, and variable 2, which is marriage happiness, are independent. Now, in this context, independent means that there's no relationship. Our null hypothesis is always a statement of no difference. So in this case, the null hypothesis would mean, independence in this case means that there is no relationship between gender and marriage happiness. So the null hypothesis is always a statement of no difference. In this case, we're going to say there's no difference between the 2 variables. The way we write it is, and this is the test for independence. And we use the word independence there, you can see it. If there is no difference between these two variables, then we would expect these conditional proportions here to be the same. We would expect these conditional proportions to be the same, and we would expect these conditional proportions to be the same if there's no difference, if the two variables are independent of one another. We see some differences, however. So we're going to run this test to see if those observed differences are statistically significant. Okay, let me finish up the hypotheses here. We know that these two hypotheses are competing. And so if the two variables are not independent, then we would say that they are dependent. And what we mean in this case is that there is a relationship. Now, this is another one of those tests that says, there's a relationship, but it doesn't go on to say, what that relationship is. We have to look at the conditional proportions to identify what the differences are. All right, there's no variables to define here because we're not using variables. That's one of the things that we're not going to have to do. The next step is to identify the level of significance, and there's no difference in this. A lot of times it's just identified in the test itself, or if not given, you can specify alpha to be 0.05. Okay, so 3 is the one where we gather the evidence, and there is, it usually means to calculate a test statistic and a p-value. And usually we have a calculator function to do that. All right, so there will be a classical approach for this one, and there will be a p-value approach, as before. I mentioned that the sampling distribution is not a t-distribution or a z-distribution. The classical approach will use a chi-squared distribution. And the degrees of freedom here, we're going to create a matrix that holds all of our frequency data, equals the number of rows minus 1, and then you're going to multiply that by the number of columns minus 1. So if we had what we had males and females, and then we had very happy, pretty happy, and then not so happy. So we have 3 rows, so R equals 3, and we have 2 columns of data, so the columns is equal to 2. So you're going to be calculating your degrees of freedom in a slightly different way than what we're used to. It doesn't have to do with the 24,455 number. It doesn't have to do with this one here, but rather you just create a matrix. And you have 3 rows, and you have 2 columns. So it's a 3 by 2 matrix. And it turns out when we use the calculator function, what we have to do is enter in this 3 by 2 matrix. We're going to give these 4 numbers. You don't have to give the totals over here because the calculator can calculate that for you. Now, another thing that you're going to see with the chi-squared distribution is it's not bell-shaped like our others. The chi-squared distribution is skewed right. For most of the tables that we have, it'll be skewed right. We're going to be doing a one-tailed right test only for this test. Another thing about this test statistic that you'll see is that it's always positive. So this distribution is going to start at 0 to the far left, and then it's going to get positive as we move to the right. Now here's where the critical value is going to be, and we're going to get this from a chi table. Here's the critical region. This is what's going to be established by our alpha. And if we find any value out here as our test statistic, then we're going to reject the null hypothesis. So for the chi-squared table, it's going to be read in a very similar way to the t table. You're going to have degrees of freedom coming down here. And in this case, degrees of freedom equals row minus 1 times column minus 1. We have 3 rows, and we have 2 columns. So you have 2 times 1, which is 2. So what you're going to find is that in most of our problems, the degrees of freedom is going to be a very, very small number. In this case, it's 2. So you go down to the degrees of freedom 2, and you go over to the alpha, 0.05, and the number that you find in this spot right here is the critical value. It's going to be called the chi-squared of 0.05 number. Go find this critical value from the table. By the way, you're going to have 3 pictures down here. We're not going to do this one, and we're not going to do this one. This is the only test that we're going to do, a right-tailed test in this section. All right, let me give you the grid back. There it is. What is the critical value? The degrees of freedom is 2. And if you have alpha equal to 0.10, what's the critical value? See it? Okay, I know many of you see it because I can see the correct answer. Here's degrees of freedom 2, and there's alpha 0.10, so 4.605. All right, so the critical value is 4.605. That's what would appear right here. And that's the variable name that we would use in this case. Right area is 0.10, so critical value. Okay, classical approach. Now let's talk about how you set up the p-value approach. The p-value approach. We know that we're going to use the calculator function t-test. The chi-squared test is going to ask you for where are your observed values? These are the frequencies from the sample. So it's the original values that you get. And you have to specify one of these things. And this is a matrix. This is matrix A. And then it's going to ask for the expected values. And we're going to put those in matrix B. And that's it. Then you're just going to be asked to calculate. And what it calculates is the test statistic, which is chi-square. And it also calculates the p-value. And if we're doing the p-value approach, we're going to be using the same criteria as we've used in the past. And that is if the p-value is less than 0.0 or alpha, 0.10 or 0.05 or whatever it happens to be, then we reject the null hypothesis. And if the p-value is larger than the alpha value, then we're going to fail to reject the null hypothesis. Okay, recall that our test statistic is the sum of all these fractions, where you take the observed value, subtract the expected value, square that, divide by the expected value. The observed values are the O's in this fraction, and the expected values are the E's in this fraction. And E appears twice in the fraction. Okay, so what we have to do to set up this test, and you never have to change the inputs of the chi-squared test. You can leave them as matrix A and matrix B every single time. Okay, so what we want is, in our example, I'll just use the marriage happiness. These numbers in here, those 6, this is a 3x2, 3 rows, 2 columns. We're going to put these values in matrix A. And then we're going to run the test, and I'll show you how to calculate the expected values as well. Okay, so here's what you want to do. Number 1, you want to go to the matrix menu. So if you hit the second key, and then the x to the -1, here's x to the -1. Right above it in blue is matrix. Since it is in blue, you have to hit the second and then the x to the -1, and that gives you the matrix menu. When you go there, it looks like this. Let's say this calculator doesn't have any matrices yet, but this one here, let's see, matrix, yeah. This one here has all kinds of matrices in there. Okay, what I want to show you is that matrix A is a 2x3 matrix, and matrix B has to be the same size, but it's not the same size in this case. So, and I've got some other matrices in here as well. So, the second thing is you want to go over to Edit. There's a menu right here, Edit. So we're going to scroll over there. And then you can select matrix A. And this is saying that you want to edit matrix A. So with this highlighted and then selecting matrix A, just hit enter, and it takes you into this screen here. All right, let's go enter in. So we have a 3x2 matrix here. So I have to change the dimensions, 3 rows and 2 columns. So for this first number, I'm going to hit a 3 and then an enter. And then I'm going to hit a 2 and an enter. And then that sets up the matrix to give me the number of spots that I'm after. All right, I'm going to enter in those 6 numbers, row by row. So I'll start with the 7609 number, and then the 7942 number, and so on, until I have all 6 of these numbers entered into this matrix. So the matrix looks like this. So you'll have to do this step at the beginning of every one of these tests. You have to enter in a new matrix A to reflect the table. 3, enter in all matrix frequencies till you have the matrix. And then you want to quit, second and then mode. When you do those 2 keys together, you quit. This takes you back to the home screen. All right, so that's the observed values. Now we got to consider the expected values in matrix B. But here's how you calculate the expected values. Our original assumption is that our 2 variables are independent. So if we're assuming that they're independent, then we can calculate the expected values, what we would expect these numbers to be, based on the observed frequencies. And so here's how you calculate expected values. You're going to see notation like this. The expected value that appears in row 2, column 3. I suppose I should switch those around. Row 3, column 2 would be indicating like this. So what is the expected value here? E32. The observed value of this cell is 460. The expected value you get by multiplying the row total times the column total of that cell and divided by the total, or the sample size. So let me say it again. You take the row 3 total and you multiply that by the column 2 total, and then you divide that by the whole sample size. All right, so here's the 460. In this case, if you take the row total, 719, and then multiply that by the column 2 total, 12,849. Multiply those 2 numbers together, and then divide by the total, or the overall total, or the sample size, and you get this. So you'd have to do that 6 times to calculate each one of these 6 expected values. Quit. All right, so I'm going to just go ahead and quickly calculate this one. 719 times 12,849 divided by 24, 455. All right, so this is 377.77. I'll just round it to 3 decimal places. There it is. All right, so these calculations are somewhat tedious. And then once we have the observed matrix and the expected matrix, we can then calculate our test statistic. But the calculator needs all the O values and all the E values in order to calculate the test statistic. All right, now we have it in there. Now I'm going to run the test. The first thing I want to show you is that matrix A is a 3x2 matrix, but I have not yet entered in any of my expected values. I calculated one, but I didn't actually enter them in. If I did, then matrix B would also be a 3x2 matrix. It is not at this point. But I'm just going to wait on that, and I'm going to go run the test. So we're going to go to Stat, and then Tests, and then we're going to select the chi-squared test. So now we're getting into running the test itself. This is the one. Yeah. All right, Stat, and then Tests. And then we're going to go down to chi-squared test. For me, it's option C on my calculator. There is another chi-squared test, but this was one of the sections, 12.1, that we skipped. It was originally on the syllabus, but we're a little behind. So that section got us. But don't use this one. Use this one here. Notice it's all set up, ready to go. So we're just going to come down and calculate. Now, don't worry that we haven't entered everything in for B, because when we hit this calculate here, the calculator is going to calculate all those expected values and dump them all into matrix B. So here it goes. As before, we get the test statistic and we get the p-value. All right, so this is another one where we need to read it from right to left. It's in scientific notation. If you really wanted to write it out, that's what it would look like. But we usually just round it to 3 decimal places, or we just say p is less than 0.001. So we never select an alpha less than 0.001. All right, now when I'm going to go back to the matrix menu, so look at how matrix B has changed after I run this test. Notice now that my matrix B is a 3x2 matrix. So it calculated all those expected values and then dumped them into matrix B. I'm going to type in, come down here to matrix B so that it goes to my home screen, and then I'm going to hit enter just to show you that these are the expected values that it calculated, and we calculated one. Do you see it? The 377.773. Row 3, column 2. There it is. So if you're asked to calculate an expected value, you know how to do it. Wherever that cell is located, multiply the row total times the column total on the top, and then divide by the total. And that gives you the expected value. All right, so the rest of it, step 4. And for step 4, we're going to reject the null hypothesis because p is less than alpha. So that step is not changed. We're going to base our decision on this. If we did the classical approach, 61.118, if this is 0, and this is 4.605, 61 and some change is going to be way over there. So it's clearly in the reject region. And then step 5 is the conclusion. So step 5, I'm going to require a little bit more from you because all this test says is that there's a relationship between the two variables, marriage happiness and gender. It doesn't say what the nature of that relationship is. So you're going to have to go look at the conditional proportions to decide how you're going to make the conclusion, or where the differences occur. And we've already done that. So, you know, here you can say that there's evidence to support the claim that there's a relationship between marriage happiness and gender. Then you need to go on further and say what that difference is. So you'll say something like, females tend to be twice as likely to respond to the prompt, not so happy in their marriage than men. And men tend to be a slightly more likely to respond very happy in their marriage than women. Okay, I have in the notes, I have these notes that you can go read, but I've also done a couple of additional examples. So you can see a couple of additional examples from this section in the lecture notes. So, and here's the calculator. Functions will be on here as well. And then there's a couple of other examples, one on prenatal care. You know, do mothers who unintend a pregnancy wait to get prenatal care? And then there's another one where they looked at Democrats, independents, and Republicans and asked them, you know, do you have a positive or a negative reaction to the word socialism? And so there's another one there. So you're going to see tables of frequencies in all of these examples. And we're going to get this value from a new table. And the table is going to read in a very similar way to the T table. The regions, okay, I don't have to extend because this one stops right at 0, but this is the do not reject region. And the only thing we can reject is a null hypothesis. We can never reject the alternative hypothesis in a test. So here's the classical approach. And let's do this example here. If we have degrees of freedom is equal to 4, and we have alpha is 0.05, we're going to go to the chi table and go down to the degrees of freedom equal to 4. Just like the t table, we're going to go over to the column that gives us the right area of 0.05. And where the row and the column intersect, this is the critical value. And that's the critical value that we're going to put right here. All right, so I don't know if you have access to it right now, but in e-learning, I did put a copy of this table. It's the chi-square table. So here's the chi-square distribution. And all of these numbers in here, just like the t distribution, these are all critical values. Critical values for a different chi-square distribution. So here's the 0.05. So we're going to look in this column. And there's the degrees of freedom equal to 4. So see where those two match up. And you get this number right here. I don't know that you can see it very well, but it's 9.488. So 9.488. So that number goes right there. Now, as before, we would then run this calculator function, find the test statistic, and then plot the test statistic on this horizontal scale somewhere. Your reference points are over here to the left, is where we start 0, and then you've got the critical value. So if your test statistic was 4.5, you'd plot it right here, somewhere between 0 and 9. If your test statistic was 16, well, you'd plot it over here somewhere. Okay, one last thing. How to calculate the degrees of freedom in this test. We're going to have a table, and the table has a certain dimension to it. In our example here, we have 1, 2, 3 rows and 2 columns of data. The degrees of freedom is always equal to the number of rows minus 1 times the number of columns minus 1. So let's say we have 3 rows and 2 columns. Sometimes I'll write it just row minus 1 times column minus 1. So rows equals 3 and columns equals 2. So I'm going to put 3 in there for R, and I'm going to put 2 in there for C, and this is 2 times 1, which is 2. And what's important here is that you do not count the total column and the total row. That's not part of the actual data. So row 1, row 2, row 3, column 1, and column 2. And we would say this is a 3 by 2, we're just going to call it a matrix. It's like a grid. Okay, if alpha equals 0.10, and we have our example, our marriage happiness example, we'll go find this critical value from the table. By the way, you're going to have 3 pictures down here. We're not going to do this one, and we're not going to do this one. This is the only test that we're going to do, a right-tailed test in this section. All right, let me give you the grid back. There it is. What is the critical value? A couple of answers there. Remember, if we have 3 rows and 2 columns, the degrees of freedom is going to be 2. So take to the table, the degrees of freedom is 2. And if you have alpha equal to 0.10, what's the critical value? So here's degrees of freedom 2, and there's alpha 0.10. So 4.605. Critical value is 4.605. That's what would appear right here. And that's the variable name that we would use in this case. Right area is 0.10, so critical value. Approach. This is the one where we're going to use the calculator function. We're going to ask the calculator to construct the p-value and the test statistic for us. All right, so first of all, the test statistic. It's a chi-squared test statistic. And our author puts a little 0 as a subscript indicating that that's the test statistic. All right, so this is going to be a very complicated formula. You have to add up a bunch of fractions. And those fractions are of the form. We're going to take the observed frequency and subtract the expected frequency, square that number to make it positive, and then divide by the expected value. Now we'll get into the weeds, I think, a little bit more later on once we do this, but just today I want to just let the calculator calculate that. So the O that you see in here are the observed frequencies from the original table. So here they are. These are the frequencies, these numbers here. And the E's are the expected values. And these values, I'm going to say values as opposed to frequencies, but expected values that correspond to the observed values. And here's how you calculate each one. There's going to be two subscripts here, and the way that you calculate them, this means the expected value in row 1, column 2. Row 1, column 2. That's what the subscript means. All right, and so what you're going to do is you're going to take row 1 total and multiply that by column 2 total, multiply those two subtotals together, and then divide by n, the sample size, and that becomes the expected value. So you'd have to do that 6 times for our example here, because there are 6 different frequencies, 6 different counts in our table. So there's going to be 6 different expected values. All right, just kind of giving you an overview, and we'll get into that a little bit more detail later. But also continuing on the step 3, and for this one, you want the calculator to calculate everything. And this one is the chi-squared, and you never have to change the inputs of this. The observed values we're going to put in matrix A, and the expected values are going to go in matrix B. And that's it. If you look at this test statistic, that's what you need, all the observed values and all the expected values. Then it can calculate. And there's no sign in the alternative hypothesis, right? I think you might have to calculate the degrees of freedom, or it might just do it for you. You don't have to worry about it, but that's it. And then it'll calculate the chi-squared test statistic, and then it'll also calculate the p-value. Now, this requires that the very first thing that you do is to enter the frequencies of the contingency table into matrix A. And if you always enter your frequencies of the contingency table into matrix A, if you do that, then you never have to change these calculator inputs over here. All right, so here is our matrix A in our problem. I'm just going to go back to this one here and write down those numbers. 7609, 3738, 259, 7942, 4447, and 460. The other thing I want to calculate by hand here is one of these expected values. So let me just calculate the expected value. All right, our notation is this. It's the expected value. It's in row 3, and it's in column 2. I'm going to put the row total here and the column total here. So what we would do is we would take the row total, 719, and multiply that by the column total, and then divide by the total, the sample size. And, you know, this number should be fairly close to the 460 if there's no relationship between these two variables. If it's different, then we should expect to see a statistically significant difference. All right, so 719 times 12,849 divided by 2, 4455, and we get 377.773. All right, so this is rounded. And, you know, that's quite a ways away from 460. So again, we know that we've seen some differences in this data. And here's another way that we can see it. Expected values are quite different. All right, let's go to the calculator and enter in the matrix. So right above the x to the -1 key, right down here, is the matrix. So you have to hit second and then x to the -1, and those two together give you the matrix. I think they just spell it out. So this is what the menu looks like when you go there. And then second, we're going to edit matrix A. There's matrix A. I've got lots of other matrices in here. You might not see anything in here. Maybe you don't have any matrices in here, but we're going to move over to edit. All right, now here's where we have this 3 rows and 2 columns. So dimensions, 3 rows by 2 columns. So the first 2 numbers I need to enter here are the numbers that establish the size of the matrix, that is the dimensions. So I'm going to hit a 3 and then an enter and then a 2 and an enter. And you can see that it creates those 6 slots for me to enter in the numbers. Okay, so enter matrix frequencies. And you got to do it row by row. All right, so here they are. So 7609 and 7942 and 3738 and 4447 and 259 and 460. So get them all in there. And this is the first step when you're running the chi-squared test. Enter the matrix. And then you want to quit the matrix menu. And you can do that by hitting the second key and then the mode key. Together they represent quit. Okay, there we are. Now we have to enter the observed values in matrix A, and then we have to enter the expected values in matrix B. However, since the calculator has all the information that it needs to calculate these expected values, you don't actually have to calculate them by hand and enter them yourself into matrix B. So I do want to show you my screen here. Notice that my matrix A is a 3 by 2 matrix and matrix B is a 2 by 2 matrix. They have different dimensions. All right, now I want to go ahead and run the chi-squared test. We're going to do this. First thing you have to do is to go enter in matrix A. Now, the calculator doesn't know that you want expected values at this point. It's only after you run this test that the calculator then says, oh, they're doing this test, they want the expected values. I need to calculate the expected values in order to calculate the test statistic. So if you go to B right now, you're not going to see, it has even different dimensions. You're not even going to see the expected values. But after you run this test, you're going to see that this matrix changes dimensions to 3 by 2, just like A. And then inside matrix B, you're going to have all the expected values. So use the calculator to calculate, and the chi-squared test to calculate the expected values. All right, let's take a look at how that would work for us. All right, so we're going to go to the chi-squared test, and we always go to the same place, hit the stat key, and then move over to tests. And then you want to scroll down to one that looks like chi-squared. All right, so there it is, chi-squared test. This one was one that we're skipping. It was from section 12.1, but we're running out of time, so we're not going to do this one this semester. But we will do the chi-squared test for independence. So notice the setup. There's nothing you have to do here. You don't even have to calculate the degrees of freedom. Even though we know the degrees of freedom is 2, the calculator will calculate that for us. So always leave A in the observed, always leave B in the expected with the brackets around them because this calculator understands those to be matrices, and then come down to calculate. It's going to calculate for us the test statistic, 61.716, and the p-value 0.000. Right, so this is 3.9671 times 10 to the -14. So it's hugely close to 0, if that makes sense. Very, very close to 0. A lot of times we'll just say p is less than 0.001. And notice it did give us the degrees of freedom when it calculated it for us. So it's a little bit different in this one, but step 4 is the decision. And the decision is the same that we've been working with in the past. That is, if p is less than alpha, then we reject. Alternatively, if the chi-squared test statistic is greater than the chi-squared critical value, and if p is greater than or equal to alpha, we're not going to reject. On the graph, that's going to be the test statistic is going to be somewhere between 0 and that critical value. And then 5 is the conclusion. So in the conclusion, the best thing that you can say is that the variables are independent or they're dependent, but you really should go on to describe the scenario and say, what are the observed differences that you noticed when you calculated the conditional proportions? All right, so if we link this then back to our results here, very small p-value, so we know that there's a difference. So in order to identify those differences, we need to go back to our conditional proportions here. And the differences are, here's a big one, and there's 4 percentage points in here maybe. So you'd say something like this. Let's see, what did I do with the, all right. I didn't write it here, but usually, or as we've done in the past, so it helps us to make, to write the conclusion, is we're going to put the claim next. And most of the time, the claim is going to be in the alternative hypothesis. That's the research hypothesis. In this case, we want to show that there's a difference between men and women and as to how they would respond to a question about marriage happiness. All right, so since I put the claim in the alternative, we're going to say there is evidence to support the claim. Right, so that's kind of the start. And now we got to say something about, you know, the differences between males and females in that question. All right, so we could just use the dependent language. Gender and marriage happiness are dependent. All right, I'm actually going to require a little bit more than this because I want you to tell me what that means. And the easiest way that you can tell me what that means is just to look at the alternative description here, that there is a relationship between these two variables. So you could say this, or you could say gender and marriage happiness are related in some way. So one of those two. Now, if you are going to say that there is a difference somehow, then you should use the conditional proportions to state what the differences are. So I think for this one, we can compare these two numbers, and we could say that females respond at a much higher rate, that they are not too happy, and that males tend to be rate their marriage themselves as very happy in their marriage at a higher rate than female. All right, so you could say something like this, and if you needed to, you could provide some evidence for that. All right, so a little bit different, particularly when we're using the calculator function, doing the p-value approach. I provided some notes in the text or in the e-learning site, and this goes through expected value, the test statistic, the hypotheses, and here's how you say the hypotheses. Here's the test statistic that we identified, observed minus expected squared over the expected, the classical approach. With the graph, notice it's always one-tailed to the right, tells you the calculator function to use, the decision, and then the conclusion. Now there's one other test, and this is the chi-squared test for homogeneity of proportions. And so in this particular test, you'll see that it's similar to the way that we give you an example like this today, but we'll work on some other examples moving forward. And for this one here, you're just going to say the proportion of the first group is equal to the proportion of the second group, is equal to the proportion The third group, if there are more proportions, we could extend this, P4, P5. There's no requirement that there need to be just 3 different groups. And to counter that, to a competing hypotheses, if the null hypothesis is saying all of these proportions are the same, we can negate that if we just say that one proportion is not like the others. So we'll say it in words. At least one of the population proportions is different than the others. It could be just P4 is different than P1 through P5. But the procedures that we use are identical. You still put in the matrix, you still run the same test. And if I went too quickly through the calculator stuff, here are the steps. You know, enter matrix A first, then quit, then go run chi-squared test, and eventually it would give you the test statistic and the p-value. There is no confidence interval for this one. I mean, we have to have a, you know, we've got 6 different proportions for this test, and some of them you might even have 10 or more. So, you know, we're not calculating a confidence interval to estimate a single thing. So there's certainly more than 2 proportions. So we wouldn't want to do a confidence interval to estimate a difference between 2 of the 6 proportions. All right, the last thing I want to show you, and is I mentioned it, but I didn't quite come back to it. All right, after you do this, now I want to take you back to the matrix menu. And do you notice now that B has the same dimensions as A? B and A are the same, and they weren't earlier. Now let me just type in matrix B to the screen by entering matrix B and hitting enter. And I want to show you that we did calculate one of these expected values at some point. Yep, here it was. We calculated the expected value in row 3, column 2 to be this number right here. But notice that if I scroll over here, there you see that number. 377.77. Not only did it calculate that expected value, it calculated the other 5 expected values. So if you want to find expected values, and I'm sure in the homework they'll ask you to calculate just an expected value, then the quickest way to do that would be with your calculator.